And welcome back. We're going to be looking at a very special function today. We're going to be looking at it in a slightly different way too. There are several ways of describing the e to the x function, and this one will be with the Taylor series. First, let's just a reminder of what the e to the x looks like. And we've seen it before. We know how to take its derivative, and I just wanted to show you a new way. Well, it's not new, but it is a way that is new for you. In order to do that, I have to remind you of another thing, and that is this. And it looks rather amusing. You see a 9 with an exclamation point there, but what it really means is just 9 times 8 times 7 times 6 times 5 and so on. And the joke, of course, when I was growing up was that you just say it really loud. You'd say 5, and but it really just means 5 times 4 times 3 times 2 times 1. So that's fakultet in Swedish, and in English, factorial. So the reason we need that is because in the Taylor we get this, and when we have that, it can look a little scary at first, but really 1 factorial is just 1, because it's, well, 1. 2 is 2 times 1. The 3 is 3 times 2 times 1. So it's not really very complicated. It's just a kind of shorthand in mathematics to help us, because as you can see in this Taylor series, this is going to go on forever. The next one would be x to the 4th divided by 4 factorial, and then x to the 5th divided by 5 factorial, and so on. It just keeps going on. And if you want to deal with the first few terms, it's quite convenient to write it in this form, although 2 doesn't. 2 times 1 is just 2. So, but we need to show you the pattern, and that's why we need to implement it this way. All right, let's look at what we have. We know that e to the x can be shown in this Taylor series this way. So we're going to have our f of x be e to the x, and then we're going to take the derivative of it, and we're going to do it bit by bit, piece by piece, just like we've done before. We know what we will end up with if this is true, but let's just look at this term by term. So what is the derivative of 1? Well, 0. What is the derivative of x divided by 1? 1. What is the derivative of x squared divided by 2? Well, the 2 comes down, it plays along with the 2 downstairs, and you end up with just x. And of course, we want to see this pattern, so I'm going to do something, and you'll see it'll make sense in just a bit. It's necessary to do this. X divided by 1 is still x. So I haven't really changed it, but it'll make sense in a second, so give it a minute. Let's take the next derivative. There we go. The 3 came down, played with the 3 downstairs, and you're still left with the 2 times the 1. And we could just keep going on. The terms continue, but this shows you the pattern. Now, we don't need the 0 out in front. I just wanted to show you bit by bit what was going to happen. So let's clean this up. There we go. And now you see something interesting, don't you? You see that, and of course we knew this before. We knew from the definition of the limit that f of x is the derivative of itself. It's a very interesting and useful property. It always reminded me of a funny song. I'll put the lyrics of it at the end of this so you can read it, because it's like being your own grandfather or something. You have the original father function, you can take the derivative and you get the son, and you can take the derivative again, you get the grandson, and they're all the same. So I always found that rather amusing. Now, what does it mean to be your own derivative? Well, if we look at the curve again, and then let's just take a place where we have the tangent, okay? And here I'll try and illustrate it, try and get it there, almost straight. Okay, I put a tangent right here. So our x was this, and then the value of the f of x was going to be right up here. The slope of this kind of blue line there will be the value that you can read off right at the point over on the y-axis. No matter where I choose it, no matter where I put the tangent, the slope of the tangent could be read off right on that. You'll be hard-pressed to find any other function that does this. It's a very interesting and useful property, and we'll be using it a lot. It will allow us to do a great many things later on. Right now, it's mostly a curiosity, but that's because we haven't gotten to the point where we can actually use it, but we will. So I'll give you the next page, and I'll just let the tape run for a bit, and I hope you can read it because it's really funny, and maybe it'll help you to remember this Taylor series and how f of x is its own grandfather if you want to see the derivatives that way. Okay, thanks for listening.